All right, so quiz 3, number 4. What a lot of folks do with this, I was pretty lenient on the points for this, but one thing you need to do right away is draw on all your lone pairs. And you also need to think about the 3 ways you can stabilize a molecule, a carbocation. It's hyperconjugation, pi bond resonance, and lone pair resonance. This also takes into account, do you recognize that this lone pair is actually in an sp2 orbital? This lone pair is not doing resonance. It's not able to do resonance. So that was one of the things that people really wanted to make that do resonance, which it can't do. So that one cannot do resonance. What I was looking for was to be able to connect the dot that here's this lone pair that could be part of this p orbital system and do resonance. So you could have done this a couple of ways. 1, 2, 3, 4. You could have done it a couple steps at a time. No problem there. And a lot of folks got to this, but they just didn't take it a step further, right? The step further, right, is actually to do the lone pair resonance. When we do the lone pair resonance, what you'll notice is that now, despite having a plus charge on the oxygen, everything has a full octet. Lots of things I saw. People trying to use this. That, right? That's that. We're connecting things. I knew this was going to be a hard question. We're connecting things. I wanted you to look at recognize hybridization state. What hybrid orbital is this lone pair in? What hybrid orbital could one of these lone pairs be in? This hybrid orbital is in an sp2 orbital. This lone pair was in a p orbital, or one of them could be. Right? The other thing I saw a lot of people do, you didn't balance charge. Right? And we'll talk a little bit about this opportunity I'm going to have about this resonance kind of worksheets or points back to revisit some of those things. It's so important to understand resonance, just to understand moving electrons. So again, this is the most stable resonance structure. Why? Everyone has a full octet. Oxygen has a plus charge, but that's okay. Doesn't matter. Octet rule is the most important. So here we have an unsymmetrical epoxide. It's unsymmetrical because carbon 2 is more substituted than carbon 1. So we have an epoxide that's unsymmetrical. We need to think about, do we have acidic or basic conditions? You see a Grignard, you should immediately think basic, because a Grignard, right, could be redrawn, essentially like this, right? It's a carbanion. Let's make that 4 and 5, 4 and 5. So basic conditions. When I see basic conditions, I think it's going to be all about sterics, right? Think like SN2 reactions, right? That's actually what we're going to do. We're going to do an SN2 reaction, right? We're going to do a one-step nucleophilic substitution. Carbon 4 reacts with carbon 1. That breaks the bond between 3 and 1. Make sure you start arrows at electron density, right? Make sure you're really clear on how you want to draw arrows. Right? If you have any questions about that, we got to talk right away, right? We got to figure that out right away. All right, so that's an SN2 reaction, right? Because, right, it's coming from the back side 180 degrees away. So the way we could draw this, there's O minus. All right, there's a hydrogen here we didn't draw on before. Carbon 4, carbon 5, 1, 2, 3. And again, these are there. We didn't draw them in, but they're there. This ethyl Grignard came from the back side, right? So it's an SN2 reaction. You get an O minus, which it looks an awful lot like a tetrahedral intermediate. If you have a tetrahedral intermediate, what do you ask yourself? Do I have any good leaving groups? Do you have any good leaving groups here? Nope. So the next step would just be protonation. So you get that alcohol. Number of carbons, number of all atoms even. 2, 1, 4, 5. Right? So make sure we have everything along the way. Didn't lose any carbons. So let's take the exact same epoxide, this unsymmetrical epoxide, more substitute carbon 2, less substitute 1. And what would happen if we were in acidic conditions? How do I know it's acidic conditions? Because it has HI, H+, and water could work. Any of those things could work. The key is essentially in acidic conditions, the epoxide in the first step is the nucleophile, not the electrophile. Right? And in basic conditions, right, this carbon is pretty electrophilic because carbon-oxygen bond's polar, and this is in a ring strain, right, three-membered ring. But in this case, HI is such a good electrophile, H+. Always use H. If you have H+ around, use H+. It's an electrophile. The other thing must be the nucleophile. Where is the epoxide electron rich at? What's electron rich at? It's lone pairs on oxygen. So that's what it's going to do. It's going to react there. So what is that? That's just a protonation, right? Now, why do we do that? Well, that makes this carbon-oxygen bonds even more polar, right? You're essentially activating that, right? You're making that oxygen a lot more unhappy. 1, 2, 3. And we also end up with I minus, right? Now in acidic conditions, it's different. It's different because think about which of these bonds could stabilize, which one of these carbons, 1 or 2, could stabilize a delta plus, right? Something being electron deficient. Not a carbocation, but just electron deficient. So really this is an argument about hyperconjugation. So carbon 2 is much more delta plus in acidic conditions. That's right. And the way it's going to react, guess what? Drawing some lone pairs. It's going to react in a SN2 fashion. No carbocation intermediate, just like a bromonium ion. We did those before, just like the bromonium ion. So SN2. And what's that going to give you? Well, there's your OH. There's iodine. And nothing changed. Right, that H was there along for the ride. It's still there. Hatched. Number our atoms. 1, 2, 3. There we're at with our new alcohol. And notice, of course, it's trans to the iodine. Now, does it matter because this carbon 1 has 2 H's? It doesn't really matter, but you can always draw it this way to show that you understood that this was an SN2 reaction, an SN2 mechanism, that you get a trans product.